All right, I stopped the last video in a little bit of an awkward spot, so I'm just going to pick up exactly right where I left off. And where I left off is we were calculating the A and B parameters for the mixture in the Pang-Robinson equation of state or the van der Waals equation of state, or the other equations of state that use the same A and B parameters. Recall that in general, A1 and A2 are going to be different depending on which equation of state that you use. But I was also looking over my notes, and I'm going to backtrack on putting the superscripts here, because A2 is going to be the same as A2 regardless of whether it's in the liquid or vapor phase. So A2 corresponds to the A parameter for pure component 2, which does not depend on composition. So because it's a pure component parameter, I'm not going to put the subscripts on A1 and A2. However, A for the mixture of the two components is going to depend on vapor or liquid, so that is going to remain the same. Now, I mentioned in the last video that when we're calculating what A21 and A12 are, we oftentimes say that they're equal to each other for simplicity, and we say that that is equal to the square root of A1, A2. And I mentioned that that is not the most accurate thing, but it happens to be one of the easiest things that works reasonably well. And to kick off this video, I'm going to start with a way that you could increase the accuracy, and this involves fitting an experimental parameter to this cross term. We call this the binary interaction parameter. To increase accuracy, we can introduce the binary interaction parameter. So the way this comes into the model is instead of saying that the cross term A, so instead of saying A12 is still equal to A21, but instead of the square root of A1 times A2, we further multiply it by 1 minus K12. And this K12 is the binary interaction parameter. And the idea is that this would be fit this with experimental data. So you need some data here, but when you have this data, remember A1 and A2 are determined by pure component properties. So A1 is a function of T and P T critical and P critical for van der Waals, and is a function of T critical and P critical and a centric factor omega for Pang-Robinson. So in other words, T critical, P critical, and omega, the acentric factor, are all look-upable. You can look those up in a table, and those are purely predictive. Purely predictive. And this introduction of this binary interaction parameter includes some way to make it fittable with experimental data. So again, it's a way to make it more accurate. If you have experimental data, you can go ahead and predict or fit this value of the K, and then that'll make your model fit better. Note that when K12 is equal to 0, I have the old term, the old geometric mean. So this changes things only very slightly. Instead of these terms, you would just go in and multiply by a 1 minus K12 here. And this is the more general form of the equation to write it like this. And then if you don't have experimental data, you could go ahead and assume that K12 is equal to 0 such that it cancels out. No such binary interaction parameter is needed for the B parameters, only for the A parameters, and that can increase the fit. All right, I feel like I've talked about a lot of stuff. Let's go ahead and now talk about when you plug all this stuff in, what do you get? All right, so in order to do that, I'm going to pause the video again and then write everything very carefully. Take a sip of your coffee before I write this, because when I write these equations, I am sure your head is going to spin because of how complex they are, but don't worry, I'll try to explain them best I can when I return to the video. Well, once again, before I do this, the only thing I'm doing is I am, let's see, where are the equations? I am solving this guy. So I'm plugging in P taking the partial derivative with respect to the number of moles, integrating with respect to z. I'm going to skip all these steps, by the way. I don't mind if you not able to follow all the steps. The important thing is what is it in the end, and the important thing is that how it came to be. The equation itself is complicated enough. So depending on the equation of state, once again, plug in P, the expression for P. So van der Waals equation of state or Peng-Robinson equation of state. And then also plugging in with the mixing rules for AM and BM. This is what you get. So one moment. Okay, here are the equations. I just want to make a couple of quick notes. This initially confused me when I was first reading this. This is, again, you would use this to calculate the mixture fugacity coefficient of species I. So this could be either component 1 or component 2. And recall that both of these equations, you have one of them for the liquid phase and one of them for the vapor phase. So both equations good for vapor phase or liquid phase. And of course, depending on whether you're doing the vapor or liquid phase, you have to add subscripts. So like, for example, if you're doing the vapor phase fugacity coefficient, it's ln, or the molar volume of the vapor phase. So just add subscripts wherever appropriate, keeping in mind also that the A and B, the A's and B's for the mixing parameters are going to be different depending on the mixture. Also, this A12, so if I'm doing component 1, for example, this is A11 is equal to A1 for I is equal to 1, or A21 is equal to A12 is equal to square root of A1, A2, 1 minus K12 for I is equal to 2. And same thing for this other one. So if I is equal to 2, I've got A22 is equal to A2, or if I is equal to 1, I have A12, which is equal to A21, which is equal to all this stuff. All right, to close out this video, I kind of just want to bring it full circle and review a little bit of how you would go about solving the problem. I've got something small planned for video number 3 today, and then I like keeping Fridays free for problem solving days. So we'll do some example problems on Fridays. I kind of like that weekly rhythm of Monday content, Wednesday content, Friday videos. But let's say that we wanted to, the equation or the problem that we'll solve on Friday has to do with, again, predicting the vapor-liquid equilibrium of a mixture. So that's a very general, broad statement, but remember that predicting VLE involves calculating the bubble point and the dew point. So I have to decide whether I want to do a TXY type or a PXY type, and depending on which one I choose, I will either set the pressure or the temperature. So once again, recall that by Gibbs phase rule is always a good place to start with thinking about what you know. Remember, one of my main theses in this class is relate what you want to know to what you do know. So by Gibbs phase rule for a binary mixture in vapor-liquid equilibrium, tells me I've got 2 plus 2 minus 2 is equal to 2. 2 degrees of freedom. So let's say we want to do the PXY curve. So for a PXY curve, you must set temperature. You must set T. So that takes care of one of the things I have to set. And then the other thing I have to set, I don't want to set pressure and then solve for X and Y, because then it wouldn't be a PXY curve, really. Well, I guess it would, but you couldn't solve the constraints. So you must set T. You do both of them. So for the bubble point P's, you would set X. Remember, I'm sorry, what is it? Bubble point, you say the constraint is Y, so you set X. And for the dew point, you would set Y. So there's 2 separate calculations that you have to make in order to predict the vapor-liquid equilibrium curve. But the main idea here is that you're setting 2 things. You're setting T and X, and therefore you have 2 unknowns. All right, so your unknown for the bubble point would be unknown P and Y. And for the dew point, your unknown is P and X. So it seems like two equations, two unknowns, but because, remember, when we have the equation of state brought in to solve for P, I'm going to have to differentiate between PL and P of the vapor. So even though these things are going to be equivalent, as we'll see in a second, I have to count them both as unknowns. So pressure of the liquid phase, pressure of the vapor phase, and Y. What are the three equations that I have to solve for these three unknown variables? I've got three equations to solve for PL, PV, and Y. So we'll just take the first one, for example, and I want to calculate what the bubble point pressure is. These are my three unknowns. My three equations are then my phase equilibrium criteria. So before it was Raoult's law, remember Raoult's law was the phase equilibrium criteria for the ideal case. I'm not in the ideal case anymore. So my first equation is x1 times phi1 for the liquid hat is equal to y1 phi1 for the vapor. So this is my phase equilibrium criteria for component one. So I'll use computer notation with the hashtag. So this is a comment. Phase equilibrium criteria for component one. My second equation is going to be my phase equilibrium criteria for component two. So it's x2, which is 1 minus x1, phi2 for the liquid is equal to y2, 1 minus y1, times phi2 hat for the vapor. Phase equilibrium criteria for component two. And then my third equation that I have to write, it seems trivial, but pressure of the vapor is equal to the pressure of the liquid. So this has to be true at equilibrium. So this is condition of mechanical equilibrium. And if two things are in phase equilibrium, they have to be in mechanical equilibrium as well. And that's also something that we've known already, that if two things are in phase equilibrium, the pressure of the phases as well as the temperature of the phases are equal. So if I were doing the reverse, if I were doing the TXY curve in which I've set pressure, then temperature of the liquid and temperature of the vapor become unknowns. And I have an equation here that says TV is equal to TL, equilibrium. All right, so again, three equations, three unknowns. If this were material energy balances, I would say my system is specified appropriately, and I could go about solving those equations. Now, of course, you see how, again, deceptively simple these equations are, because in order to find, most of the magic is in finding what the phi's are. We also have to set what equation of state we want to use. So let's just say we say for the van der Waals equation of state this is, by the way, general, and I want to highlight that. So this is for the general case, very general. Doesn't matter which equation of state we have. Doesn't matter anything about the model that we're doing. This is very general for the PXY case. All right, so they say for van der Waals, the pressure of the volume equaling the pressure of the vapor would mean that if I wrote both things, I've got RT over V under bar L minus BML minus AML over V under bar V square is equal to RT V under bar V minus BM of the vapor minus AM V over V vapor square. All right, so it looks like just by solving this one equation, PV is equal to PL. Remember, the only things I'm specifying here are temperature and X, right? Because I want to solve for Y. So T and X1 are set. And I have to go through this entire exercise for T and Y1 being set. But look at all the unknowns that it looks like I've introduced here. I have to now solve for the molar volume of the liquid. So how do I get that from the van der Waals equation of state? Well, I have to solve for it. That becomes something I have to solve for. So most of these equations have hidden things in them that you have to solve for. What about the fugacity coefficients? To solve for the fugacity coefficients, you would have to plug in the equations that I just wrote up here. So this is the van der Waals equation, the van der Waals mixture fugacity coefficient. I would have to plug this entire thing in. And in this equation, remember, only T and X are set. So I have to know what the molar volume is, which I hopefully have solved for before with that Pang-Robinson, or with the van der Waals equation of state. And I also have these van der Waals parameters A and B that I have to solve for. But remember, they're only a function of the critical pressure and temperature of the components. Oh, by the way, this Pang-Robinson mixture fugacity coefficient, I have to scroll because I couldn't fit it all on one line. So the textbook, by the way, I want to tell you where this is in the textbook. In Sandler, this is equation, I want you to know this so you can double check it. Let me look up what equation it is real quick. I don't think this van der Waals one is in Sandler. So I'll just zoom out a little bit. How about that? So Sandler, this is equation 9.4-10, and Dom-Invisco, it's 12.59. So this is probably not very clear at this point. I don't expect it to be super clear at this point. I think this will help a lot to see an example problem played out in Microsoft Excel. And like I said, I'll plan one of those for Friday. But in the third class for today, I wanted to just briefly cover what would happen if you, instead of doing phi-phi modeling, you could also do gamma-gamma modeling, in which case you would model both. Well, I'm just going to get to it in the third video. How about that? We're going to call this video complete.